Okay, in this video, we'll look at how processes are executed. In today's lecture, we discussed about C programming, and we know that C programs are compiled and linked, and executables are created, which are nothing but machine language code, which is now, after the compilation and linking process, it still resides on the disk, and eventually when you request the operating system to execute your process, then it is loaded in the memory. Now this picture I have taken from a lecture by Professor Chris McDonald, and in subsequent slides I'll use much simpler pictures, but here it is interesting to look at the different parts of the memory. This is the memory that has been allocated to the process. As we know, every memory location has an address, and this is the low address end of the memory for the process, and this is the high address end. Now, there are several things here which I will briefly go into before I come to the main interesting part that I want to discuss, and that is this part of the memory image of the process. However, there are other parts. In particular, at the high end of the memory, we have first of all command line arguments. We haven't discussed it in details today, but when you execute your C programs, you can pass command line arguments to the programs. For example, it may look like this. Your executable is called a.out. That dollar symbol is nothing but your shell prompt, and you may write a.out blank f and press the return key or the enter key. Now what it means is the operating system understands that this f is a command line argument. Most probably it is a name of a file that you want to read from or you want to write to, etc. So there is a possibility of passing different arguments at the start of the execution of the process. Now there are other things called environment variables. Environment variables inform the operating system about the rights and privileges of your process. In all processes in the Linux operating system, for example, are created by their parent processes. For example, when you do this, you write a.out f and press the enter key. The cell where you are doing this sort of thing or typing this command itself is a process, and as soon as you press the enter key, the cell creates a child process, and that child process is from then onwards, through some sequence of actions, the child process gets this executable code which is sitting in a.out and starts executing that code. Now the environment variable from the cell is inherited by the child process, and the operating system now knows what is to be done when, for example, your process wants to do some input-output. So whenever there is an input-output request, your process makes such a request. The operating system will figure out from the environment variable where that input-output is being done and whether your process has the privilege or the right to do that input-output. It must be, if you are writing a file, it must be either on your console or in the home directory that has been allocated to you. Now after that, there are several parts. The interesting part here is the code. After all, execution of a process is nothing but execution of the statements, machine language statements of that process, one after another, and hence the machine language code should sit somewhere, and here it is. And then there are data that are associated with your process. For example, you may declare global variables that are at the top of your C code, which are all outside the main function or outside any function for that matter, and they are initialized and loaded here. So this is the overall picture of the execution environment of a process. Now we'll try to understand what is going on in this part in particular, and that is of interest because that really gives you a mental picture of how programs are executed in the computer. So let us draw this picture again. For example, we have drawn, my drawing is not that good. So here was the stack. Imagine a perfect drawing. However, these lines are only like a cartoon. They don't have any other purpose than to indicate what is going on here. So this is the stack and this is the heap. Now let us look at a simple C program. I'll not write the entire program, but for example, I'll not write the include statements that appear at the very top of your C program, but I'll write a simple main, and you know the main should have a type, int main. I'm not writing anything inside, which is perfectly okay in this case. And let us assume that this main function has an integer variable I, and it calls another function called foo. Now this is the way you call functions from another function. So inside main you have a call to this function called foo, and of course let us say foo itself is defined here, where there are some statements inside foo. I should write, for the sake of completeness, I should write I equal to foo, where foo is returning an integer data type, and there is of course some return statement. Say return k. There is an integer here which is k, and return k. So doesn't look very good or very nice, but we got the idea. There is a main function here, and there is another function called foo here, and from inside main you are calling foo. Now what really goes on inside this memory segment? Now what goes on is, let us draw it a bit better here. Okay, first I'll draw only the stack. So as soon as execution starts, some part of the stack, this is the entire stack. I have simplified the picture. So this is the entire stack. So some part of the stack is allocated for the main function. What do I mean by that? What I mean is, inside the main there could be variables like I, and there could be other variables that you will declare. All those variables will be allocated space here. Unfortunately, my trouble has started. So here there will be space for I and further variables, whatever you are declaring. Now this thing is called an activation record. Activation record. So in the stack there is a space that is allocated for main. Now whenever this call is made to the function foo, another activation record is created, which is for, so another activation record is created for the function foo. And inside this activation record there are local variables in foo as well. For example, you have this local variable int k, which will be allocated space here, and so on. Now what I want to point out to you is that as function calls are made from function calls, for example, I could have another function called foo1, which is called from inside foo here, then another activation record will be created. So the stack in fact grows in this manner. That is, more and more space is allocated on the space on the stack, depending on what kind of function invocation you have in your program. So if we go and draw a better picture of the stack and the heap, what is the heap? I'll come to that in a minute. So here is the stack as I have drawn in the previous slide, and here is the heap. and the stack itself is divided into different activation records for different function calls, and the stack grows like this. Okay. Now, what is the purpose of doing all of this? The purpose is the following. When you write your program, the operating system doesn't have any idea what kind of function invocations will occur from inside your program. Though you are writing a main and a foo, you can write perhaps a loop. For example, inside main, you can write a loop for I equal to 1, I less than 10, I plus plus. My semicolons are not that good. You can correct it. And inside this loop, I am calling foo. So in this case, the operating system knows that if it wants to know, it knows that foo will be called 10 times in this loop. So it is possible to preserve space for foo in the memory 10 times the space a single invocation requires. However, in many situations, this is not the case. In many situations, perhaps you will have another variable called p here in your main, and you will read the value of p from the input, for example, using a scanf or something like that. In other words, the value of p will be read depending on whatever the user is supplying the value, and then you can have here, you can have, instead of 10, you can have p. Now consider this situation now. The operating system has no clue what could be the value of p, because p is coming as a user input. So there is no way the operating system can allocate enough space for the invocation of the function foo on the stack or anywhere in the memory. And p could be 10 at one particular time, p could be 1000 or 1 million or something like that. So this space, the activation record for a function, is important because it is like the scratch pad for the function. Whatever the function is doing, it will calculate something, it will write certain variables, and all those will occur inside this activation record of the function. So it is essential to allocate this scratch pad or this activation record for correctly invoking the functions. And the operating system doesn't have any idea at the time of loading the function, or loading the process in the main memory of the system, how many such scratch pads will be required. And hence this mechanism, the dynamic allocation of these scratch pads or activation records, which grow on the stack. That is, more and more activation records are allocated and the stack grows in this direction. So you can see that the programming language allows you to write programs of this nature where function calls or number of function invocations will be arbitrary, and the operating system has to provide a facility for allowing that. In other words, the operating system has to provide a facility for correctly executing your processes or programs. Now, that's the purpose of the stack and how the stack grows. Now, what is this thing? Okay, to explain this thing, actually we haven't touched upon this aspect of C in the lecture, in today's lecture. So this is the old picture I am drawing again. You can imagine the stack has different activation records and it is growing in this direction, and this is the heap, which is at the lower end of the address and which is growing in this direction. That is, more and more space is allocated on the heap, and heap takes on more and more space in this direction. Now the heap is used for allocating dynamic memory. Now, if you are not new to C programming, you know that many times it is necessary to allocate dynamic memory for your program. One good example would be when you are storing a certain number of items from user input. That is, user is inputting a certain number of items, and it is possible that sometime the user will input 100 items either from the keyboard or from a file, and sometimes the user will input 1000 items. Now, it is difficult to allocate space statically, that is at the time of the writing of the program, unless you know exactly how many items will be input by the user. And there is no way you can know that, because you have written a program that is as general as possible, so the user could input any number of items like this. In those situations, we allow, or the C language allows you to allocate memory dynamically through a system called, actually this is a wrapper around a system called malloc. We'll come to that later, perhaps briefly in the next lecture. Now all those dynamic memory is allocated here in this part of the memory, which is called the heap. What is the connection between the stack and the heap? Actually, stack and the heap is connected quite logically, because after all, whatever you do in your C program is done from inside a function. Either it could be the main function. Let us assume that this is the activation record of main and this is the activation record of foo, and you have allocated dynamic memory from foo. Now whenever you allocate dynamic memory from foo, that memory is allocated actually inside here in the heap, and a reference of that memory is held by this function foo here. Now dynamic memory is used for doing intermediate computation, for storing results, and eventually foo returns, and this activation record is deleted. I'll come to that in the next slide in some more details. And this dynamic memory either has to be deleted or deallocated. If it is not deallocated, this link, once the function invocation is complete, this link is lost. And the dynamic memory that has been allocated here is called garbage. And garbage is a problem because if your program creates garbage more and more, that is memory in the heap more and more, which doesn't have any reference in the stack, then your memory or the heap will be filled up, and eventually the stack and the heap will collide. And that's a bad thing, because at that point the operating system aborts your program execution. So I'm perhaps going a bit far from what I wanted to say. I'll stop here about discussion about garbage, and I'll go on to some more detailed look at what is going on inside the stack. But you got the general idea that heap is for dynamic memory allocation and stack is for function invocation. Okay, let's to end with, let's look at the stack again. I'll not draw the heap here, and this is the stack, and here are the different activation records. Now, as before, this is the activation record for the function foo, and when the execution of the function foo is complete, then the control returns to the previous function, because after all, foo was called from somewhere. So let us say foo was called from another function here, call it f or something like that, and the C code will look like int f. I'm not writing complete C code, and here inside there will be a call to foo and something like that. So when the execution of foo completes, the control returns to this point, the statement immediately after foo, and this activation record is removed, or it is deallocated, or it is it is lost basically. So whatever was happening inside here is lost from that point onwards. So you can see what is going on in the stack is growing in this direction as more and more functions are called, and the stack also shrinks in this direction as more and more function calls return. So the behavior of the stack is like a zigzag where it goes down and goes up, goes down and goes up, and eventually, of course, your program terminates when the last statement of the main function is executed. So at that point, the stack will be empty. That is, the activation record for the main itself will be removed, and the stack will be empty at the end of the execution of your program. So I'll stop here, and I will definitely answer any questions that you may have based on this particular video or any other videos.